This video will be a quick review of the three models of bonding. That is, looking at Lewis dot structures and resonance structures as model 1, looking at atomic orbitals and how they overlap as model number 2, and then molecular orbitals as model number 3. So let's start with a very simple molecule, just hydrogen. Here's the Lewis dot structure, not very complicated. No resonance there, obviously. So that's model number 1. Just Lewis dot structures and resonance structures. Model number 2 is a little bit more sophisticated and looks at overlapping atomic orbitals. So let's just review very quickly what orbitals are overlapping when you have a molecule of H2. Obviously in one atom you have just an s orbital, and in the other atom you have another s orbital. Each one of those has one electron because the valence of hydrogen is 1. So we bring those two orbitals together, and in essence each one thinks that it has 2 electrons in it, so it follows the duet rule. That's the basis for atomic overlap, and it's essentially why we draw the structure that way, because the hydrogen shares 2 electrons. Now what about model number 3? In model number 3, we are going to draw not atomic orbitals, because remember each one of these is still an atomic orbital. In model number 3 we're going to draw what we call molecular orbitals. Here's the thing to keep in mind. Look at the number of atomic orbitals that are overlapping in your molecule in model number 2, and that's the number of molecular orbitals you're going to draw. So in essence we're going to say in one hydrogen you have an s orbital, and in the other hydrogen atom you have an s orbital. Those can combine with each other in 2 different ways. In one case, they can combine to form one orbital that covers both nuclei. Okay? This is what's called a sigma orbital, and it's called that because it's a combination of 2 s orbitals, sigma being the Greek letter for s. But there's another way in which these 2 can overlap. Excuse me, not overlap, but another way in which these 2 can combine, and that is they can essentially repel each other, and you then get a molecular orbital. Now notice this is one molecular orbital. It happens to have a node in it, and it's a little bit higher in energy than this one. This is called a sigma star orbital, and the asterisk or star on there simply refers to the fact that it's a non-bonding orbital. Now what do we mean by non-bonding? Well, if you have an electron in this orbital, let's use a dot. In fact, there are going to be 2 electrons in there, as represented by those 2 electrons right there. If there are 2 electrons in this orbital, electrons being negative and nuclei being positive, those will essentially act as glue and bring the 2 nuclei together, so that's a bonding orbital. But if you have electrons in either of those 2 lobes, or in fact it's really both of them at the same time, notice that there's no electron density or very little electron density in the middle, so the positive nucleus on this hydrogen and the positive nucleus on that oxygen, on that hydrogen, are essentially staring at each other with no electron density in between. Like charges repel, so they tend to fly apart. So this is why this is called an anti-bonding orbital. Okay, and that's why it has a star on it. Now just to be clear, how can the 2 molecular orbitals be derived from these 2 atomic orbitals? Well, if both of these happen to have the same phase, and remember orbitals are waves, so they can have a phase. If they both happen to have the same phase, like let's say for example both positive, then those positively reinforce each other, essentially build on each other, and produces a blob that looks like that with an overall phase of plus, or minus if these both happen to be minus to begin with. But what if they happen to be opposite phases to begin with, one positive and one negative? Well, then they destructively interfere. They, in the middle where they would overlap, there is no wave there because they're destructively interfering with each other, and therefore you end up with a space in between with no electron density in there, and the 2 phases of this orbital then are positive on one side and negative on the other, and thus we have a node in between. So these are the two molecular orbitals that can be derived from these two atomic orbitals. Remember that rule, it's very important. The number of molecular orbitals that you can make will always be the same as the number of atomic orbitals that you're overlapping. Okay, furthermore, we have essentially two orbitals here at two different energies. So we have the sigma orbital at this level and the sigma star orbital at that level. Let me put those over here just to be clear about it. Here is the sigma orbital, here is the sigma star orbital, considerably higher in energy. Now, here's the question, how many electrons do we have to put into that scheme? Obviously, 2 electrons. Where are they going to go? Remember the Aufbau principle that says that you build up from the bottom. That applies whether it's atomic orbitals or molecular orbitals, energy levels, and they build up from the bottom. So where will those 2 electrons go in the ground state? In other words, the most stable form of it would have both electrons in a sigma or bonding orbital, no electrons in an anti-bonding orbital. That explains why hydrogen is a stable molecule, because all of its electrons are in bonding orbitals. Now here's an interesting question. What if we shine light on it at exactly the right wavelength to boost an electron from the lower to the higher orbital? So here we go. We're going to zap it with energy in the form of light of exactly the right wavelength, and we boost an electron into the higher the higher molecular orbital at this point. What does that do to our molecule? Well, we still have an electron in a bonding orbital, but we also have an electron in an anti-bonding orbital. Those tend to cancel each other out, and therefore the molecule is much weaker, doesn't have any propensity to stay together. So you can actually make hydrogen split into 2 atoms by shining light of exactly the right wavelength on it, boosting an electron to an anti-bonding orbital. This is what's called an excited state, where the electrons are in a higher state than they would be if they were as low as possible. And when they're as low as possible, that's what's called the ground state. So this is an excited state. Okay, so we've seen this is a very simple model for hydrogen. This is a not much more complicated model using atomic orbitals overlapping. The molecular orbital model is a little bit more complicated, but explains things like why you can shine light on molecules and make them fall apart. Okay, well obviously hydrogen is a very simple molecule. Let's do one that's just a little bit more complicated. Let's look at a methane molecule. Obviously, the Lewis dot structure is very simple. So that's model number 1. That's really all there is to that. What about model number 2, overlapping atomic orbitals? Well, first of all, we have to decide what orbitals are there on each of these atoms. Obviously, the the hydrogens each have just an s orbital. What about the carbon? What kind of orbitals does it have? Well, if you look carefully at that carbon, you'll quickly realize that that's an sp3 hybridized carbon. And so the carbon atom has 4 orbitals arranged tetrahedrally, one pointing down here in the plane of the blackboard, one pointing down there in the plane of the blackboard, one coming out in front, and one going back behind, all at angles of 109.5. So this is an sp3, another sp3, another sp3, and another sp3. And then of course we have the 4 hydrogens, each one of which has an s orbital. And how many electrons do we have to put in all together? Well, count them off of your Lewis dot structure. 1, 2, 3, 4 pairs, which is 8 electrons. Obviously then, I'm going to use red. 2 there, 2 there, 2 there, and 2 there. Each orbital, all of the s's and all of the sp3s, are filled with electrons. And so that's that, quote, happy situation, and it explains why methane stays together. But that's a pretty simplistic picture. What we really want to do is look at molecular orbitals. So how are we going to come up with molecular orbitals that are going to involve all of these atoms, 1 carbon and 4 hydrogens? Well, here's how we're going to do it. We're going to look at each of these bonds individually as if it's a separate part of the molecule. And, for example, this hydrogen and carbon, an overlapping of an s orbital with an sp3 orbital, we are going to consider that and look at its molecular orbitals. So 2 atomic orbitals, we're going to come up with 2 molecular orbitals. So how could they overlap? Well, remember here is what an sp3 orbital actually looks like. It's got a big part and a little part. Those are opposite signs because there's actually a node right through there. That's what an sp3 orbital looks like. What about the hydrogen? Well, if the hydrogen with its s orbital happens to have the same phase as the fat part of the sp3 orbital it's overlapping with, then those will combine, constructively interfere, and we'll end up with, of course that's a carbon atom there, we'll end up with a big part and a little part, and the big part will cover both the carbon and the hydrogen, and the little part, of course, will just be over here like a little tail sticking out there. And notice that now electrons in this orbital will be mostly in between the carbon and the hydrogen. They will act like glue to hold it together. And so this is a bonding orbital. And we're going to call it a sigma orbital. Now, if sigma is the Greek letter for S, why do we call that a sigma orbital if it's a combination of an S and an sp3? Well, one reason that you can think of there, or one justification for that, is that both of these orbitals have the letter S in their name, and therefore we're going to call it a sigma orbital. That's bonding, so we don't put the asterisk on it. But what's the other way that an sp3 on a carbon, with its little positive, little negative and big positive parts, can overlap with a hydrogen in an s orbital? Well, what if the big part of the sp3 and the phase of the s on hydrogen are opposite to each other, so one positive and one negative? What would happen if we combined those? Well, then we get something that looks like this. Negative on that part of the orbital, positive on that part of the orbital, negative on that part of the orbital. And notice that this end has two nodes in it. By the way, this sigma orbital only had one node in it. It's always going to be true that as you go from a lower energy to a higher energy orbital, you're going to increase the number of nodes. So this one only had one, this had two. Remember back to our hydrogen situation, the sigma orbital didn't have any nodes, the sigma star orbital had one node. So we're increasing the number of nodes. What about bonding or anti-bonding here? Well, notice that there's very little electron density between the carbon and the hydrogen in that orbital. And so this is actually an anti-bonding orbital. So again, just to review, two atomic orbitals overlapping, an sp3 and an s, and two new molecular orbitals, a sigma and a sigma star. Again, you always make the same number of molecular orbitals as you started with atomic orbitals. But that's only part of the picture for methane, because of course we have not only that overlap of an sp3 and an s, but also that, and that. So how do we handle that? Well, essentially these other three sp3 overlaps are exactly the same as this, sp3 overlap. So we're going to draw an energy diagram, just like we did for the hydrogen molecule, in which we have not one, but four sigma orbitals down low in energy. They all look just like this one right here. They're all bonding orbitals. And we have four sigma star orbitals, all at the same energy, and they all look just like this one. So essentially we have two molecular orbitals for this bond, one sigma and one sigma star, two molecular orbitals for that bond, one sigma and one sigma star, two molecular orbitals for this bond, one sigma and one sigma star, and two molecular orbitals for that bond, one sigma and one sigma star. And then the only thing we have yet to do is put in electrons. So how many total electrons do we need to put into this molecular orbital diagram? Well, 8 electrons as shown in the Lewis dot structure, 8 electrons as shown with pink dots in that structure, and so 8 electrons here. Here's how we'll put them in. 1, 2, 3, 4. Remember, we always spread out electrons in degenerate orbitals, and these are indeed degenerate orbitals, all the same energy. And then we go back and start pairing them up. So 5, 6, 7, 8. So total of 8 electrons, all in bonding orbitals, none in anti-bonding orbitals, and therefore the molecule tends to stay together. Essentially the same explanation as we had for the hydrogen molecule. What I've drawn here is a ground state. You can imagine an excited state in which we shine light at exactly the right wavelength on the molecule. What happens? We boost an electron from the lower to a higher orbital. That would be an excited state, and it would be weaker than the ground state because you're now putting an electron into an anti-bonding orbital, which tends to make the molecule weaker. So again, if you shine light at the right wavelength on methane, you can actually split it into pieces using exactly the right wavelength. So that's the picture using 3 models: Lewis dot structure, overlapping atomic orbitals for model number 2, and then molecular orbitals. And I've drawn the molecular orbitals there and shown their energy levels over here. That would be model number 3. Well, I think you can imagine for just about any saturated molecule, we're going to have all sigma bonds. So let's just summarize, and we won't do the whole picture, but what about for an ethane molecule? There's the Lewis dot structure. Here is a quick drawing for the model number 2. That is the atomic overlap picture. Again, model number 2 is nothing new. You've drawn balloon pictures before. We're going to have hydrogens bonded on each of these atomic orbitals. So there's the balloon picture. If we put in pairs of electrons, of course, we'll have 2 there, 2 there, 2 there, 2 in between, representing the single bond between carbons. 2 here, 2 here, and 2 there. And so all of the orbitals are filled, everything follows the octet rule, or in the case of the hydrogens, the duet rule, as we've seen before, and therefore that's a stable molecule, and that's what model number 2 suggests is the picture for ethane. But now we want to get a little bit more sophisticated and look at molecular orbitals. The only thing new here is that we have a sp3 overlapping with an sp3. The rest of them are all just s's overlapping with sp3s, and so they will be low-lying sigma and high-energy sigma star orbitals, just exactly like the ones we saw for methane. But the difference is now we have another type, overlapping of an sp3 atomic orbital with an overlapping of another sp3. What will that give rise to? Well, that will also give rise to 2 molecular orbitals, one of which will be a sigma, and we'll put a subscript of sp3 on it to show that it's a different type of sigma than an sp3, which is what the other ones were. We'll also have a higher energy sigma sp3, and that'll be a sigma star, just like we saw sigma star sp3s in the case of methane, and also in the case of all 6 of these bonds over here. Now, besides those 2, we will also have how many more sigmas at the bottom and how many more sigma stars at the top. Well, there are 6 more overlapping s and sp3 orbitals, so we'll have 6 more sigma s sp3 and 6 more sigma star s sp3. Now, even though the sigma sp3 is not exactly the same energy as the sigma s sp3, we're just going to draw them all together at essentially the same energy level there, because they're all way down in energy compared to other things we'll talk about here in a minute. And same thing with the sigma stars. We're just going to bunch them all at the top, because essentially all sigma molecular orbitals have close to the same energy, not exact. Now notice, how did I know how many orbitals to put in at the bottom and how many to put in at the top? Well, let's count the bonds. 1, 2, 3, 4, 5, 6, 7 bonds. And therefore there will be 7 sigma orbitals at the bottom and 7 sigma star orbitals at the top. Really what we're doing is not counting bonds as much as counting orbitals, because remember the rule says you have to have as many orbitals, as many molecular orbitals at the end as you started with atomic orbitals at the beginning. So let's count atomic orbitals. How many atomic orbitals in this picture of model number 2? Well, let's count the s's first. 1, 2, 3, 4, 5, 6 s orbitals. And then 1, 2, 3, 4, 5, 6, 7, 8 sp3 orbitals. Now here's a hint. Every carbon atom will always have 4 orbitals on it, whether they're sp3, sp2 and an extra p1, or sp and 2 extra p orbitals. There's always going to be 4 orbitals on any carbon atom. And there'll always be 1 orbital on a hydrogen atom. So it makes it easy to count orbitals, essentially 4 for this carbon, 4 for this carbon, and 1 for each of the 6 hydrogens. That's a total of 4 plus 4 is 8, plus 6 is 14. 14 orbitals altogether. That means we need 14 molecular orbitals altogether. And it turns out they're split evenly, 7 at the bottom and 7 at the top. 7 sigma orbitals, 7 sigma star orbitals. And that's how you can predict the energy levels, the energy diagram where the orbital is laid out on it ahead of time before you even really worry about what types of orbitals they are and what they would look like. And then the last thing to do, of course, is count electrons and put them in. How many electrons altogether? 2, 4, 6, 8, 10, 12, 14. Electrons, 7 pairs. Well, interestingly enough, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons, all in sigma orbitals. It always works out that way, that all of your orbitals, at least in the ground state, as long as all you have is sigma and sigma star orbitals, all of your electrons will be in the bonding orbitals, none will be in the anti-bonding orbitals. Okay, so now we've seen what it looks like for ethane, and you can simply do any other alkane that you want to in essentially the same way. So you should be able to draw the molecular orbital scheme, both sigma and sigma star orbitals for propane or for butane or for any other alkane that you might want. And that includes like cyclohexane and cyclopentane and molecules like that. You simply count the number of bonds, or actually the number of orbitals, which will be twice the number of bonds, lay them out with half of them at the bottom and half of them at the top, label these sigma, label those sigma star, and that's your electron diagram or your energy diagram for the molecular orbital scheme. Now we want to do one that's just a little bit more interesting. What if you have a double bond in your molecule? Like, for example, ethane. Let's do that molecule. Well, there's model number 1, all done, just Lewis dot structure. Model number 2 is the overlap of atomic orbital model, or what I commonly refer to as the balloon picture. So how does that look? Well, each of these carbons is, of course, sp2 hybridized. So we're going to have an sp2 pointing that way, and an sp2 pointing that way, an sp2 out in front, and an sp2 back behind. And again, remember that's planar, that's trigonal planar, so these are 120 degrees away from each other, all in the same plane. And the carbon next to it has to have its orbitals also in the same plane. So this is sp2, 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 sp2. And each of these carbons, because they're sp2 hybridized now, and here's where the new thing comes in, they also have a p orbital. So here's a p orbital, and I'm just going to use green for a p orbital, just to make it look a little bit different. But don't forget, that's also an atomic orbital, and it's also on the carbon, so really it's no different from the sp2s. It just happens to have 2 lobes, one on top and one on bottom, one positive and one negative. And so that's a total of 4 orbitals on this carbon. 1, 2, 3, plus the p orbital makes 4. Same thing over here. And so this is a p orbital, but those are still atomic orbitals located on a particular carbon. And then, of course, we have the hydrogens, each with their s orbital, overlapping with these atomic orbitals. And then we can look at the pairs of electrons. Of course, there's a pair in here, and a pair in here, and a pair in there, and a pair in there, and a pair in the p orbitals. But of course, the p orbitals are actually overlapping. They don't look like it in this kind of a picture because we have to draw them kind of skinny and far away from each other, but in fact they're really much closer together and much fatter, so they actually are overlapping side by side. And I represent that by these curved lines showing the overlaps between the p orbitals, and you've seen that kind of thing before. Okay, so there's, oh, and I forgot, we also have 2 electrons in this overlap. Okay. Now we call this kind of overlap sigma overlap, and we call this kind of overlap sigma overlap. What do we call it when we have 2 p orbitals parallel to each other? P orbitals parallel, we call those pi, so that's a pi overlap. And by the way, we use these Greek letters sigma and pi to represent two slightly different things. In model number 2, we use them to represent the kind of overlap between atomic orbitals. When we get to model number 3, which is the molecular orbitals, then we use the sigma and the pi to actually as the names of orbitals. Those are molecular orbitals. So let's just lay out a scheme for all of the sigma and the pi orbitals for ethylene. Well, first of all, how many molecular orbitals will we have altogether in our energy diagram? Well, if we count total orbitals in this picture, we have 4 on this carbon, 4 on that carbon, plus 1 from each of the hydrogens, so 4 plus 4 plus 4, that adds up to 12. So we should have 12 molecular orbitals in our diagram over here in model number 3. How will they look? Well, notice that we have 5, one here, one here, one here, one here, and one here, that are sigma overlaps. So that means we're going to have 5 sigma orbitals at the bottom. 1, 2, 3, 4, 5, and we're going to call those sigma orbitals. Actually, they're not all exactly the same because this represents a sigma sp2, sp2, and these 4 represent a sigma s sp2, and they are slightly different in energy, but essentially all the same. So we're going to put them down at the bottom. Those are 5 of them, and then we'll have 5, 2, 3, 4, 5 sigma star orbitals at the top. Again, one of those is a sigma sp2, sp2 star. The other 4 are sigma s sp2 star orbitals. But again, we're just going to essentially assume all sigma orbitals are the same as each other. Okay, but that's only 10, and we know that we have to have a total of 12 molecular orbitals. Where do the other 2 come from? Well, they come from overlapping p orbitals. So let's take a minute and look at how p orbitals can overlap with each other. So here are 2 carbon atoms, and I'm going to draw them much closer together this time. There is some overlapping of sigma orbitals in between, or sp2 orbitals in between to form a sigma bond, but notice that these p orbitals overlap with each other. Okay. Now, what would happen if we assume that both top halves or lobes are positive and both bottom lobes are positive? Then they're going to smear out, they're going to constructively interfere, and we would end up with a big fat lobe on top and a big fat lobe on the bottom, positive and negative. How does that affect the molecule with the electrons in there? Well, the density isn't exactly in between the carbons, but essentially up here acting as bridges, pulling them together. So electrons in this orbital are bonding electrons, and we're going to call that a pi orbital. So we use the Greek letter pi when you have p orbitals parallel to each other. So this is called a pi orbital, and it's a bonding orbital. But how else could these 2 p orbitals overlap with each other? Well, one could be positive on top and negative on the bottom, and the other one could be negative on the top and positive on the bottom. And in a situation like that, then they destructively interfere in the middle, and you'll actually have an extra node, as we've seen before, an extra node, and the molecular orbital is going to look like this, positive, negative, reflecting the positive, negative of the atomic orbitals. But remember, these are molecular orbitals. This is all one orbital, it happens to have 4 parts to it. This is a molecular orbital, it happens to have 2 parts to it. This has a node through here, this has that same node, but then it has an additional node up and down. This is just showing the atomic orbitals that those molecular orbitals came from, so I'm going to erase that right now. And this one, if there are electrons in this orbital and spread out over those 4 parts, it's not going to keep the molecule together at all. In fact, in many ways forcing it apart. So that's what we're going to refer to as a pi star orbital. So we have a pi and we have a pi star arising from these 2 p orbitals. Again, the number of molecular orbitals, 1, 2, has to be the same as the number of atomic orbitals, 1, 2. Now the only other question is, where does the pi and the pi star orbitals go on our molecular orbital scheme over there? Because remember, so far we only have 10 orbitals here, and we know we need a total of 12, and that's because we still need to put in the pi and the pi star orbitals. Where do they go? Well, I'll tell you. It turns out that they are closer together in energy than the sigmas are, and they are symmetrically disposed around the middle of the molecule. So it's kind of like a mirror image. The bottom is a mirror image of the top of the molecular orbital scheme. This is your pi orbital, lower in energy. This is your pi star orbital, higher in energy. Okay. Now we need to put in electrons. So how many electrons total in here? Well, you can count them on this picture, or you can count them on this picture. 2, 4, 6, 8, 10, 12, or 2, 4, 6, 8, 10, 12. We need a total of 12 electrons in there. Here they go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, all the bonding orbitals are filled. None of the antibonding orbitals have any electrons in them, so it's a stable situation. The molecule tends to stay apart. Now, what about an excited state? Notice that in an alkene, as opposed to an alkane, the two orbitals, the lowest occupied molecular orbital and the highest unoccupied molecular orbital, are much closer together than they are in an alkane. In an alkane, you only have sigma, so they're way far apart from each other. You don't have any pi, so there's nothing in between. But when you start having pi orbitals, then you make it easier to boost an electron from this orbital to that one. In other words, this energy gap is much smaller than this energy gap, and therefore it's easier to attain an excited state. And alkenes tend to absorb light of longer wavelengths than alkanes do. Longer wavelengths, remember, meaning less energy, and that's because it takes less energy to boost an electron from a pi to a pi star. And there we go. We can explain that fact much more readily using a molecular orbital scheme than we can using either of these two orbital schemes. Okay, that's a good introduction to molecular orbitals. We'll stop at that point for this video, and then we'll do another video shortly which involves a conjugated diene, and we'll see what its molecular orbital scheme looks like. Thank you for your attention.